This is Chapter 15, Our Galaxy, for Astronomy 100. In this chapter, we're going to look at the Milky Way and its features, galactic recycling, the history of the Milky Way, and finally, what the galactic center may contain. So in section 15.1, our goals are, what does our galaxy look like, and how do stars orbit in our galaxy? Here's a view toward the center of our own galaxy, the Milky Way. Obviously, we can't take a picture from the outside because we're in it, and to actually go outside or to travel outside our galaxy would take thousands and thousands of years, even at the speed of light. This is how the Milky Way galaxy appears in our sky as a faint band of light. This is probably a time exposure over several seconds or a minute, so that we can see a lot of the structure of the Milky Way galaxy. In the Chicago area, this would be very difficult, but in more rural areas, we can actually see a band of light across the sky, and that is looking toward the center of our galaxy. So we have dusty gas clouds that obscure quite a bit of the view toward the center. It's called interstellar medium. Here's a diagram of what our galaxy probably looks like. We have the disk, which is the main feature going left to right across, and we're located, our sun and our solar system is located in the disk, about 27,000 light years out from the middle. At least that's what we think. The bulge is the sort of spherical area in the middle. There's the halo, which is mass of stars and clusters around our galaxy, and the thickness of the disk is roughly about 1,000 light years. So put that all together and we have a galaxy roughly 100,000 light years in diameter. Again, this is a schematic view or a diagram of what we think it looks like, but based on observations of other galaxies we think are similar in size, and we've been able to see their structures, this is what we think ours looks like. This is another artist's concept of what our galaxy probably looks like, with the spiral arms, the disk kind of angled from lower left to upper right, the bulge somewhat spherical, and the halo, those are the other stars and clusters around the Milky Way, the center of the Milky Way galaxy, in sort of a spherical cloud. So how do stars orbit in our galaxy? Well, we have several types of stars classified by where they are. We have disk stars, which is what our sun is, one of many, many disk stars. We have halo stars, which are orbiting in many directions and orientations in this cloud or spherical cloud around our galaxy. And we have the bulge stars, which are closer in toward the middle and sort of a spherical mass. The halo stars and bulge stars seem to orbit with random orientations, whereas the disk stars maintain their orbit in a slightly random movement, slightly up and down movement, but they stay within the disk. So stars in the disk all orbit in the same direction too, with little up or down, with just a little bit of up and down motion. In the bulge and halo, they both have random orientations. So what does our galaxy look like? It's consisting of a disk of stars and gas, with a bulge of stars at the center of the disk, surrounded by a large spherical halo. And how do stars orbit in our galaxy? Well, stars in the disk orbit in circles going in the same direction with a little up and down motion. The orbit of the halo and bulge stars, though, have random orientations. Now let's look at galactic recycling. Our goals here is how is gas recycled in our galaxy, and where do stars tend to form in our galaxy? This is a diagram in Chapter 15 in your book that kind of goes through the whole cycle of what happens to galaxies as they form and reform. This is on page 386 at the top of the page. So we'll go through this quickly. It's called the star-gas-star cycle because it is a cycle, and gas goes to star, star goes to gas. So we recycle gas from old stars into new star systems. Here's an example of a high-mass star having a very strong stellar wind, a solar wind, that actually blows bubbles of hot gas out into space. Lower mass stars return gas to interstellar space through stellar winds and planetary nebulae, but they're not as strong as a high-mass star stellar wind. This is a picture of X-rays from hot gas in a supernova remnant that reveals newly made heavy elements. So this is where we get the notion that the heavier elements, heavier than iron, would be elements that would be derived from a supernova explosion, a high-mass star. A supernova remnant remains cool and begins to emit visible light as it expands, as you see in the pictures in A and B. The new elements made by the supernova mix into the interstellar medium. So as you see in part C, the graph, there's ionized oxygen, neon, hydrogen, sulfur, and nitrogen. So this is just one example of the kinds of elements that we might find as a result of a supernova remnant. If multiple supernova explode at basically the same time, they'll create a pretty hot bubble that can blow out of the disk of the galaxy. These gas clouds cool in the halo, and then they come back down. The gases actually re-enter the disk. So we have atomic hydrogen forming as hot gas cools, allowing electrons to join with protons, and then molecular clouds form next, after gas cools enough to allow atoms to combine into molecules. So the governing process here is temperature, the amount of heat the gases have. Start with atomic hydrogen, which is very, very hot at the time, and then as the gas cools, we get molecular clouds, molecular hydrogen, for example. So here's some examples of molecular clouds. This is in the constellation Orion. You can see the three belt stars of that constellation, and within it you can see some of the more colorful clouds of gas that are in the constellation. Gravity forms the stars out of gas in the molecular clouds, and they complete the star-gas-star cycle. So we get atomic or atoms, we get molecules, and finally we get gravity bringing things together to form stars. Radiation from these newly formed stars is eroding, in this case, these star-forming clouds. So we're actually getting a combination of things happening here. So here's a good summary. The stars make new elements by fusion. We already know that. The dying stars give off gas and new elements, producing these bubbles. 10 to the 6th would be about 1,000,000 kelvins. And then the hot gas cools, allowing atomic hydrogen to form. Further cooling permits molecules to form. And then last but not least, gravity forms these new stars, and of course the planets with them, in molecular clouds. So we observe the star-gas-star cycle operating in the Milky Way's disk using quite a few different wavelengths of light. A through G here are all labeled in terms of what wavelength we're looking at. Here's our Milky Way galaxy in infrared and visible light. So as you can see, the visible light is blocked out quite a bit, probably with by interstellar medium. Here's a view of X-ray emissions from the hot gases above and below the disk. Up at the top of the slide here are 21 centimeter radio waves emitted by hydrogen. So this is showing where the gas is cooled and settled into the disk. And radio waves from carbon monoxide, showing the locations of molecular clouds. So we get these multiple views depending on the wavelength of energy we're observing in our own galaxy. Here's infrared, a long wavelength infrared emission showing where young stars are heating up dust grains, and gamma rays that show where cosmic rays from supernovae collide with atomic nuclei in gas clouds. So where do stars tend to form in our own galaxy? Well, we have these objects called ionization nebulae. They're found around short-lived high-mass stars, signifying active star formation. These stars don't live for long, but in the time that they do exist, and once they blow up, you see in the bottom right here the kinds of elements that they'll actually produce. Here's a reflection nebula that will scatter light from stars, and as you can see, the area around the star is kind of a bluish color. Well, that's because blue is the color that these atoms are actually reflecting. We have this halo around our galaxy with no ionization nebulae, no blue stars. But in the disk, we have blue stars. So that's a region where stars are forming. So apparently a lot of the bluish type stars are in the spiral arms of our galaxy. And this is not our galaxy, this is the Whirlpool galaxy. We're looking at it kind of from the top down. But as you can see, there are lots of blue stars in the spiral arms. So this would be the birthplace of many of the shorter-lived stars. Ionization nebulae, blue stars, and gas clouds would be found in these regions, because that's the birthplace of the stars. Spiral arms are waves for star formation, apparently. This would be a place where most of the younger stars would be born. So the spiral arms are waves of star formation. The gas clouds get squeezed as they move into the spiral arms, and then the squeezing of those clouds triggers star formation. So by their own mutual gravitational attraction, we have these clouds of gas actually forming stars. So how is gas recycled in our galaxy? Well, gas from dying stars mixes new elements into the interstellar medium. It slowly cools and makes the clouds where stars form. And those stars will eventually return much of their matter to interstellar space because they'll burn up their fusion products and they'll explode. Finally, where do stars tend to form in our galaxy? Well, there are active star-forming regions containing molecular clouds and hot stars and ionization nebulae in the spiral arms. So what's the history of the Milky Way galaxy? Well, our goals here are to look at what do halo stars tell us about our galaxy's history and how did our galaxy form. We have the halo stars, which have some of the heavier elements in them. And then we have disk stars, which have a much lower percentage of heavier elements, but still enough that we can recognize them. So we think halo stars formed first, and then they stopped. And then disk stars formed later and continued forming. So our galaxy probably formed from a giant gas cloud that gravity caused it to collapse or contract, and whatever gas was left settled into the spinning disk. So stars are continuously forming in the disk as the galaxy grows older. So the bluer stars, remember, in the spiral arms, that would be the birthplace of many of the newer stars. Halo stars formed in clumps that apparently later merged. So what do halo stars tell us about our galaxy's history? Well, halo stars are all old with a smaller proportion of heavier elements than the disk stars, indicating that the halo formed first. And then how did our galaxy form? Well, it formed from a huge cloud of gas with the halo stars forming first, disk stars forming later, after the gas settled into a spinning disk. So finally, let's look at the galactic center. What's the evidence for a black hole at our galaxy's center? This is one piece of evidence that we'll look at in just a minute. But as you can see, where we think the center of our galaxy is could possibly be a black hole. And we have these objects apparently orbiting what appears to be that black hole. So we have infrared light coming from the center of our galaxy. We have radio emissions coming from the center, and apparently those radio emissions are sort of trapped in the magnetic field lines around the galactic center. We have radio emissions from the center of our galaxy, and we have swirling gas near the center emitting infrared light. Swirling gas, as you see in letter C there in the radio image, the infrared image showing basically the same thing. So apparently we have these stars orbiting something. As you can see by the trails, there is a central object there that apparently is keeping everything in tow, and that could be a black hole. The orbits of these stars, based on their paths, indicate the mass of the black hole is roughly 4 million suns, 4 million solar masses, which is incredibly huge, which would classify it probably as a supermassive black hole. X-ray flares from the galactic center suggest that tidal forces of this black hole might actually be tearing apart matter as it's falling into it. So what's the evidence for a black hole at our galaxy center? Well, orbits of stars near the center of our galaxy indicate that we have a black hole with about 4 million times the mass of the sun.